not encouraging or advising anyone to modify their firearms. This is for entertainment and educational purposes only. What's up, everyone? This is going to kind of be a two-part video. The first is a detailed look at the full 1911 barrel fitting process. I've wanted to make this for a while to round out my 1911 technical content playlist. The second part of this video will be episode 2 of my building a double stack 1911 video series where I fit the barrel to my pistol. Some resources will be in the description. First will be a list of all the pages from the M1911 and Colt 45 Kuhnhausen manuals that deal with barrel fitting. I will link to some channels that have good videos on this topic like Hayes Custom, Mosin Virus, J. Philip Williams, Spardella Arms, and a few more, some of the classics. There are a lot of great videos out there. I don't think that I've seen one that shows the whole barrel fitting process from beginning to end with the level of detail that I want. That's what I hope to accomplish in this video. It's gonna be long, but I'll try to be as concise and clear as possible. Detailed timestamps will be provided, so hopefully you can find the information you want a little bit quicker. A reminder here that I'm not a professional gunsmith. I'm not a 1911 expert. What I present in this video will be my current best understanding of the process based on my experiences and my interpretation of the information that I've found. There may be some parts of this project that have a subjective aspect. People have different ways they go about fitting barrels, and that's fine. Please share your thoughts and experiences in the comments so that I and others may see it and possibly learn from it. If I miss something, let me know. Let's get into it. Why do we even want a nicely fit barrel? Mainly to maximize accuracy. Also, a nicely fit barrel, like a nice slide to frame fit, is synonymous with craftsmanship, higher quality, and a higher price point. Here's a neat chart from page 108 in the Colt 45 Kuhnhausen manual. There are lots of things that affect mechanical accuracy of the pistol, but if you look at that chart, they're claiming about 70% of it comes from the aspects related to barrel fit. The idea behind maximizing shot-to-shot accuracy with a tight barrel fit is to have the barrel come back into battery in the same place each time. A loose barrel that has wiggle room at lockup won't do this. Fitting a barrel is about more than just the tightness of the lockup. During this process, we also define and tune how the action unlocks and the barrel links down. This is critical to proper cycling function, reliability, safety, and the longevity of all the components in the pistol. I want to look at how the barrel is held still at lockup. All 6 degrees of freedom must be constrained. That means translation along 3 mutually orthogonal axes and rotation about those same 3 axes. At the muzzle end, the barrel is constrained from translating up and down and side to side within the clearances of the barrel OD and the slide or bushing ID. It can rotate a little bit like this, which is good because we need the barrel to tilt. It's free to slide along this axis and rotate about it. At the chamber end, a nicely fit barrel is kind of pinched between the lower locking lugs on the slide stop cross pin and the top central point of the upper locking lugs. This is called the support triangle. Translation up and down along this axis is stopped by these 2 points. And rotation, if we consider the lug contact to kind of be the pivot point, is stopped here and here. The barrel is constrained from rotating this way because the lower lugs are contacting in 2 places across the slide stop pin. If I push a circle into a circle, it centers itself into a point in line with the applied force. Now, what if both of these circles are actually cylinders? Their 2 central axes will tend to align when you push them together. At the upper lugs, a circle meets a circle and the barrel centers itself, preventing translation this way. But the upper lug surfaces are cylindrical, so that also prevents the barrel from rotating this way because of the tendency of the axes of the 2 cylinders to align. And at the muzzle end, the barrel is being pushed down into another cylinder, preventing it from translating this way and rotating this way. Well, the bull barrel cylinder is cut out on the bottom, so it's actually like contacting on two edges, but they're doing the same thing. With a bushing barrel, it's a full cylinder. Constraining translation in this direction, which we know the muzzle end cannot prevent, comes from the chamber hood and upper barrel lugs being pinched between the slide lugs and breech face. On some ordnance spec pistols, the hood doesn't contact the breech face, but this face does right here. This is unlikely on any gunsmith fit barrel. What are some relationships that don't contribute to constraining the barrel? Hood width doesn't. I mean, it could, but I don't think it's supposed to. It's generally clearanced as a final step to the fitting process. The barrel link at lockup shouldn't be doing anything. Any surface or point of these lower lugs or ramp, except for right here and right here, where it contacts the slide stop pin. This radius and kind of vertical face right here on the bottom of the lugs does contact the slide stop pin. This doesn't really constrain the barrel to the slide, it stops the forward movement of the slide and barrel together. There are quite a few special tools required for the 1911 barrel fitting process and a few that are nice to have. So I want to cover that all up front. I don't want to post a tool list with links, that's a pain. I have talked about where to get most of these things in past videos. A lot of the 1911 specific tools can be found on Brownells. You will need feeler gauges, a couple of which you'll need to modify. You need calipers, a selection of stones and files, and some fine grit sandpaper, a Sharpie or some layout die, maybe some lapping compound. Clay helps for taking lug engagement impressions, access to a mill and fixture or indicator or a jig for fitting the barrel hood length and width by hand. Personally, I wouldn't do this without access to a mill. Hood length gauge or inside micrometers. Firing pin port gauge is really nice. A lug fitting file. A lug centering block. A barrel holder and a lower lug cutting tool. A chamber finish reamer. I would recommend cutting fluid. Head spacing gauges are not necessary but may be nice. A reamer for the barrel link pinhole will most likely be needed. If you're fitting a barrel bushing, a lathe will really make that easier. This basic process is outlined in the M1911 Kuhnhausen manual, pages 125 to 135. I'm omitting quite a few details for simplicity and time's sake. There are some of these things that could be done in a different order or aren't even called out in the steps on those pages, so I'm putting them in where it makes sense to me. Again, there is some subjectivity with this order of operations, but I don't think what I'm presenting is blatantly wrong or would lead to ruined parts. The scope of this process will be limited to gunsmith fit barrels. They have extra lower lug material. Generally, these slots here are shallow. They have a short chamber and the hood is too long and too wide. I'm finding as I work through this process having a barrel and slide from the same manufacturer is nice. These are both from Atlas. Any high quality parts should be within spec, but if any barrel and slide combo are going to have dimensions and tolerances with the best chance of agreeing, they're probably going to be ones from the same manufacturer. There is technically a first measuring step that I am skipping, but I will cover it later in the horizontal bearing surface check section and explain why you're probably not going to do it. First, it's a good idea to inspect the slide, barrel, and frame, look at any contact areas between the barrel and other components, maybe lightly polish or duress the barrel passage in the slide, deburr, break any sharp edges on the lugs, but just barely, things of that nature. Muzzle end fit is important, but on bull barrels it will likely be dictated for you. The slide barrel passage spec is from 699 to 702, and bull barrel diameter is generally 693 to 695, leaving us with a diametrical clearance range from 4 to 9 thousandths. I just checked that the barrel slid in there and cleared the upper lugs on its way in. There are some comps and sight blocks that thread on and their OD will need machined to fit the slide. In a bushing barrel system, Kuhnhausen says the barrel fitting is done with a slightly loose bushing. This is the way I've seen some professionals do it too. Check that the temporary bushing doesn't interfere with the barrel as you're fitting. However, I didn't see it directly stated when you should fit the final bushing. How much of that fitting do you do with the looser bushing? I think I figured it out as I've worked through this process, and we'll put that step in where I think it goes and makes the most sense to me. Again, there may be some ambiguity or subjectivity with the order of these operations. Measure the slide hood slot width and the barrel hood width. Take material off the hood until it just slides in all the way back up against the breech face, and don't clearance it any more than that right now. The material needs to be taken off the hood evenly so it ends up centered in the slot in the slide. This Atlas barrel came with an offset hood, so most of the material needed to be removed from this side and only a little bit on this side. It makes it a little easier to keep everything centered. 25 thou needed to come off. There's no way I could keep this surface square and flat while removing 25 thou with a file. I would recommend machining the majority off, then finish the last couple thou with a file. There are fixtures for milling these hoods that will greatly reduce setup time. Everglades Ammo makes one. There is an Apex Tactical fixture to be used with a file, but it doesn't look like it'll help you keep the hood sides square. Now that the hood slides back up against the breech face, material needs to be taken off this surface until the hood slides all the way up and stops on the upper lugs in a condition called 100% vertical lockup. We want this because it will maximize accuracy by producing the tightest barrel fit. On the slide, measure the distance between the breech face and the forward locking lug. Because the lug surface is offset inward from the ejection port, a special tool is required. There are gauges for this. EGW makes one. I used a 1 to 2 inch inside micrometer. Measuring the hood length on the barrel is easy with calipers just like that. See how much needs to come off. 10 thou needed to come off this one. Again, not a good thing to do by hand. The surface is likely to wander. Machine all but maybe a thou off and fit by hand. Keep this surface as square as possible. Take a tiny bit off and check it. Sharpie on the surface helps to see if material is coming off evenly. Just take off enough material that it slides up and down freely, but does not have any play back and forth. Make sure the barrel is solidly stopping on the upper lugs and not interfering with something at the muzzle end, like the bushing skirt or the barrel passage with a bull barrel. It may feel springy up towards the top if it is. Now that the hood adjustment is done on this face and mainly done on these two, reestablish chamfers if needed, break edges, smooth it up so it won't have any issue sliding in and out of lockup easily. I got a little generous with these chamfers right here, but these other ones are more reasonable. I had to chamfer this corner, this guy, and this guy. This chamfer was still there after I removed my material, and I broke some sharp edges down around here with a stone. Now that we can push our barrel into 100% lockup, we need to check where the firing pin port in the slide ends up in relation to the chamber. Center the lower lugs with one of these blocks and put firm pressure on the barrel. You can buy gauges for this. I went ahead and machined my own. I can drop this in and see that the little nipple on the end slides right into my firing pin port without any resistance. Another way to check this would be to take the primer out of a case and fill the primer pocket with clay. The chamber of a gunsmith fit barrel will be short, so it probably won't go into lockup. You may need to trim the case shorter. Once the case is in there, you could drop the firing pin in from the back and see where it hits the clay. If it's off side to side, that might be an issue. There could be something wrong with the machining of the slider of the barrel, maybe a non-concentric chamber or a firing pin hole that's drilled off center. You're unlikely to run into this with quality parts. If the firing pin port is high, meaning the chamber is low, that's not a huge deal. Most gunsmith fit barrels err on the side of shallow slots right here. Remove some material until the chamber goes up enough to center the firing pin. If the firing pin port is low, meaning the chamber is high, the slots in the barrel could be too deep. The barrel passage diameter could be too large, meaning these lugs are too high up. It's unlikely that you'll run into this with a gunsmith fit barrel and high quality parts. So how far off center is acceptable? I couldn't find a spec, so I looked at the tolerancing on the ordnance dimensions and did some math. Remember, these diagrams are for 45 ACP chamberings and a 92 thousandths diameter firing pin. Firing pins now are commonly around 68 thou. I'm only considering the barrel and the slide relationship at 100% lockup, which is where we are at in this process. Possible deviation will increase when the slide and barrel are on the frame due to tolerance stacking of the frame rails, pinholes, pins, less than 100% vertical lockup engagement, etc. I calculated that there is an allowance for the firing pin port to be displaced from the chamber center by about 7.5 thou. So a 15 thou range in the vertical and horizontal direction based on the dimensional tolerancing of the barrel and slide mating features, clearances, and firing pin port location. This is a rough calculation. I'm guessing the acceptable operating range is a bit wider than that. If the firing pin is too far off, it may pop primers or the firing pin could be damaged, leading to all sorts of reliability issues. Now this is the point. Barrel lug slot depth would be adjusted to achieve vertical firing pin port alignment at 100% vertical lockup. Brownells makes a special file for this. It has a narrow cutting face and dead sides so that no material will be taken off the vertical faces of the lug slot. Don't cut any slot lower than 63 thousandths. You really shouldn't have to. That is the maximum slot depth according to ordnance spec. This requires that the barrel has enough extra material on the lower lugs. If the chamber goes up, there still needs to be enough meat here to cut away for proper fit with the slide stop pin. A gunsmith fit barrel will likely have more than enough. You shouldn't have to worry about it. But it doesn't hurt to check. You should really have one of these tools for this project. Use that in your barrel alignment block to make sure your chamber is in lockup. You should see lug material sticking through your slide stop pinhole. That means there's enough material there. To figure out where the lugs are contacting, mark them with a Sharpie or die chem, push the barrel into lockup, and maybe give the lower lugs a little tap with a soft mallet to make a mark. That will show you where material needs to come off. It may be easier to see what Sharpie gets left on the slide. Likely only the rear lug will be touching. Take a little off, check, repeat. Take material off evenly and try to maintain that constant radius. Don't make a flat spot or a facet. I needed to take a little material off my rear barrel lug slot to get the chamber up higher. I was able to use my 1911 slide rail file that had a narrow cutting edge and two dead sides. I want to discuss vertical lockup engagement. This is a hot topic, so keep in mind this is just my interpretation of the information I have found, but I will also be presenting my own calculation. I hope it makes sense and also doesn't have some glaring issue that completely nullifies it. I'm trying to demystify this all to myself as well. In the context of fitting this barrel, this slot is 44 thousandths deep after my adjustment. If I fit the lugs properly, I will maintain 100% engagement here, or 44 thousandths of an inch on this vertical lug face. Is that enough? This is going to be a long section, but I think it's a valuable discussion to have. Remember, timestamps are a thing. Skip it if you want. This is more broadly about assembled pistols, not just the barrel and slide relationship we've been considering so far. The fit of the lower lugs on the slide stop pin, the frame rail aggregate stack height, pinhole location, and pin diameters, etc. can all affect vertical lockup engagement. A production or ordnance spec gun with no hand fitting will likely not have 100% lug engagement. As I talk through this, I may refer to lug height or slot depth. I'm talking about the same thing, whether it's the barrel lugs or the slide lugs. These poor barrel lugs have a tough job. The cartridge case slips in and out of the chamber. There may be some friction on the way out after the round is fired and the brass is expanded. However, the majority of the rearward force that is a reaction to the momentum and energy of the round being fired and the pressure spike in the case will be imparted on the breech face via the case head. Initially, the slide and barrel travel rearward together. That initial pressure spike presses the case back into the breech face and starts the rearward motion of the slide. The barrel gets pulled along with it only by the small contact of these vertical lug faces. Let's cover some geometric and dimensional considerations and how to measure engagement. The barrel tilts down towards the muzzle end at lockup. The chamber area and slots in the slide are machined at a slight downward angle too, but probably not as much. So each lug moving forward will have fractionally less engagement. By how much will depend on the fit of the parts in the pistol. That's why lug engagement is measured here at this first lug. The forward two slots in some barrels may be deeper than the first. The slots in the slide should be clearanced for the barrel lugs. Contact should happen like this, not like this. Vertical engagement is usually given as a percentage. How much of this total face height is contacting the lugs in the slide? I don't find this very useful. For an ordnance spec barrel, these slots can be anywhere from 53 to 63 thou deep. On gunsmith fit or match barrels, I've seen this range around 42 to 58 thousandths. So 60% on one barrel probably won't be 60% on another. If you have 100% engagement, but the slot is only 10 thou deep, that's not enough. To measure engagement depth, measure down to the hood of the barrel from the top of the slide at lockup. Now pull the slide to unlock it and hold it at the point just where the barrel clears the lugs in the slide, and measure again. And then you subtract those two values. For percentage, you would divide that by your total barrel lug slot depth and multiply by 100. Another way is to put some thin strips of clay in the slots, coat the lugs with oil, talc, or graphite first so the clay doesn't stick. I got some children's modeling clay for this. It comes in fun colors, and this one tastes really good. Push the barrel into lockup or assemble the pistol and cycle the action, then take it out and check. So you can see my clay pretty much got all squeezed out at this lug right here, and indicating 100% engagement at this lug. And then right here you can see I still have a thin layer of it across the top of that lug, so that's less than 100% engagement. You can kind of like measure down to the clay surface, but it helps if the clay is a little bit more firm. Scouring forum posts, I've seen a range of minimum values from like 38 to 45 thousandths. In the M1911 Kuhnhausen manual, page 82, they claim lug damage generally occurs in pistols that have vertical lug engagement in the 50 to 60% range. But this often coincides with other issues like soft slide material, high round count, and the use of overpressure ammunition. So that 50 to 60% by itself may not cause issues. The minimum ordnance spec slot depth is 53 thousandths. 50 to 60% of that is 27 to 32 thousandths of engagement. In the Colt 45 manual, page 51, I found this, a minimum of 42 thousandths, or about 70% of a mid-spec slot depth. I want to look at this from a strength of materials standpoint. For all the following calculations, I will be using the worst case scenario to give me the most conservative and safe estimate. I am assuming that all the force imparted on the slide will be transferred to only one lug. And the highest force the lug will see comes from the initial pressure spike in the case at the instant the round is fired. It's not feasible for me to consider energy, momentum transfer, slide, barrel, bullet, and gas masses, and include all that from the moment of ignition to the time the bullet leaves the barrel. I wouldn't know how to include those in my calculations. So much is going on in those few milliseconds. Modern 1911 barrels are usually made from 4140 or 416 stainless, slides 4140, 416, and I've seen some made out of 17.4. I'll link to some sources in the description with good information about these materials and where I got some of the charts and tables I'll be showing. Yield strength refers to the stress a material can handle before it plastically deforms, meaning it deforms, then stays that way when the force is removed. These materials are ductile and tough enough that they will yield before they fracture. I have access to ASTM, ASME, SAE, and American Metal Society books at work. These are the organizations that create standards for materials, among many other things, for use in a wide variety of industries. I looked up a bunch of specifications for these materials. I will be referring to these yield strengths in KSI, that is 1000 PSI. This is commonly how they're reported using imperial units. All of these materials are heat treatable for a wide range of mechanical properties. 4140 can have a yield strength ranging from 60 to 125 KSI. That lower 60 KSI yield is from a softer hot rolled and annealed or normalized state. It's unlikely that a 4140 slide or barrel would be machined from something this soft even before coating or other treatment like nitride. 17.4 stainless. Most of the 17.4 heat treatments I generally see are around that 105 KSI value. The lower 75 KSI value comes from a quite uncommon condition H1150M heat treatment, so I wouldn't consider that one. 416 stainless has a range from 40 to 160 KSI. I deal with 4140 and 17.4 a lot for my work. I'm less familiar with 416. Atlas says my barrel is heat treated to 40 Rockwell C minimum. I looked at the yield strength and hardness ranges of heat treated 416, and the ones that were around 40 Rockwell C plus or minus 4 had yield strengths from 115 to 140 KSI. I will assume the lowest yield spec material used for the barrel or slide construction, not considering any surface treatment, is going to be 4140 with a yield strength of about 85 KSI in the softest common cold drawn and heat treated condition. That is the value I'll use for the calculations. I want to cover some relationships to make sure we're all on the same page. Pretty basic stuff here. Pressure is force applied over an area. Rearranging this, we can see that force is a pressure multiplied by an area. If a force is distributed over a smaller area, meaning a smaller denominator here, that results in a higher pressure. If a pressure is applied over a larger area, that results in more force. To calculate the force on the lug from the firing of a 9mm cartridge, I will be using the maximum average pressure for 9mm plus P ammo given by Saami, 38,500 psi. Maximum average pressure, or MAP, is defined as the recommended maximum pressure level for loading commercial ammunition. Link to this document with my page references is in the description. I will assume that when the round is fired, the case will see a spike in pressure up to that level. The pressure will impart an impulse force on the breech face proportional to the case head area. I will assume the case head is at its maximum diameter specification and neglect the chamfer, giving us the highest resultant force. 38,500 pounds per square inch multiplied by the area of the case head, which is pi on 4 times 0.394 inches squared, gives me 4,694 pounds of rearward force on that breech face that will then be transferred to a single upper lug interface, not two or all three. I'm going to be considering contact stress on this lug face right here, not shear stress along the lug surface like this. There's much more surface area in this plane to resist the shear force. The smaller area of one of these faces is more likely to deform than the bulk of a lug to shear, especially at the rearmost lug that doesn't have a slot behind it. I generally design with no less than a 2-to-1 safety factor. That means at normal operating conditions, a material should only see half of its yield strength with margin for calculation assumptions in rare, extreme operating conditions and situations. The force from the round being fired divided by the area of one of our lugs, which I am trying to solve for, is equal to the yield strength of 4140, 85,000 psi multiplied by that 2-to-1 safety factor. So this right here is going to be 170,000 psi. Solve for area, 0.0276 square inches. Cool, now I need to correlate that to the lug engagement depth. In my 3D modeling software, I've made a sketch of the locking face area using the minimum ordnance spec for the barrel OD. I can adjust the engagement depth value here, then extrude this into 3D space to measure the area of this face. I adjust that dimension and check the area until it matches the area I just calculated. This occurred at about 40 thousandths of engagement depth. My model of the contact area is idealized, so this won't be representative of the real world, where actual contact area will vary from pistol to pistol and likely be a bit less, but again, hopefully accounted for with my conservative calculations. So that's my best estimate and recommendation for minimum vertical lug engagement, 40 thousandths of an inch for 9mm chamberings. Depending on the barrel, this will result in different percentages of engagement, which is why I'm not reporting a percentage. I went ahead and repeated the calculation for other common chamberings of the 1911. The only two variables changing are the case pressure, the Saami map value, and the case head diameter, and therefore the force that the lug sees. The geometry and material properties stayed the same. For 45 ACP plus P, 41 thousandths minimum lug engagement depth. For 40 Smith & Wesson, 42 thou. For 38 Super Auto plus P, 40 thou. The same as 9mm plus P. And for 10mm auto, 46 thousandths. Out of curiosity, I ran the calc for an ordnance spec 45 ACP pistol with 60 KSI yield strength material. This is likely more representative of early production 1911 slide material, probably 1018 or 1040, 1045 cold rolled carbon steel that would have yield strengths from about 45 to 60 KSI. With the 2-to-1 safety factor, standard pressure 45 ACP ammunition, and one lug contacting, you would need 45 thou of engagement. This isn't really reasonable. That is 85% of the minimum ordnance spec slot depth. A mid-spec ordnance pistol would likely not have that much engagement. However, if 2 lugs were contacting, each would need 24 thou of engagement. That's only 45% of minimum slot depth. So there would be plenty of margin for lower yield strength materials while still maintaining that 2-to-1 safety factor. We can also probably assume that the design was intended to have more than one lug in contact, being that there's 3 of them. This was kind of a nice little gut check that my values with modern alloy carbon steel weren't unreasonable. I hope you were able to follow along with that calculation and it made some sense. I hope I explained it well enough and that my assumptions and the 2-to-1 safety factor I included seem reasonable to you. I am feeling good that the value I calculated is close to other values I've seen from multiple sources. If it was like 10 or 80 thou, I would know that I screwed up. All right, shit man, sorry about that. Back to the process. This is an optional but recommended step, but also if you find an issue here, you're probably not going to do anything about it. In this step, we will see if all 3 of these vertical lug faces are contacting their respective slide lugs at the same time. Ideally, we want all 3 lugs to be in agreement at lockup, but 2 is still better than 1, like I assumed was the case in my calculation. That measurement step I mentioned skipping at the beginning of this process, the one I said you're probably not going to do, that's the measurement to check if the barrel and slide lugs will be in agreement before you even decide to fit a given barrel to your slide. You're probably not going to do this because it assumes 2 things. 1, that you have special equipment to measure location of these lugs in the slide and barrel relative to the breech face, and 2, that you have a bunch of barrels and slides to select from. You measure up different barrels and slides and match 2 with the closest lug spacing, then proceed with fitting from there. Also, let's think about this. I'll go over how to check this in a moment, but let's say you only have 2 of the 3 lugs contacting. You would have to take a little material off the first 2 lugs to get this third one to be in contact. Well, you just changed the relationship of this lug to your barrel hood. We have already fit the hood length. You just brought the whole chamber forward by the amount that you removed from these lugs, loosening the hood fit. So that's why I say you're not likely to do anything about this, even if you don't find all 3 lugs to be in agreement. Couple of interesting historical notes here. When armorers or gunsmiths were fitting national match barrels to slides to improve accuracy, and they wanted all 3 lugs in agreement, they would equalize the lugs by removing material, then weld up the rear of the hood to add material, and fit the hood back to the breech face for no play at lockup. On ordnance spec pistols, the hood usually isn't touching the breech face, so equalizing lugs while trying to maintain a tight hood fit was less of an issue. I found this really interesting. The ordnance spec shows a net 0.002 clearance at the front lug. This apparently dates back to the days of softer, lower heat treat spec carbon steel slides. I don't know how common this practice was on an ordnance spec or other pistol back in the day. That 0.002 net clearance at the front lug shows up here. I guess sometimes they would fire an overpressure proof round to seat the rear 2 lug surfaces and bring that third face into contact. The slide would deform at these 2 rear lug interfaces. There's also a note here about how this clearance is likely not machined into commercial slides because they're made of harder material that wouldn't pressure seat anyways, so that brings us back to adjusting lug agreement by removing material, and then you run into that hood length issue unless you weld it up. Here's how you check the lug agreement at lockup. This process is outlined in the Kuhnhausen M1911 manual, page 126. I tried it and it worked pretty well for me. Sharpie or die chem the barrel lug vertical surfaces. You're not likely going to be able to see what the contact looks like just by pushing them together. Put a little bit of lapping compound on the lug surfaces after your marker has dried. Then move the barrel in and out of lockup gently a few times. The lapping compound will take the marker off where contact is occurring. We're not trying to lap the barrel lugs into the slide or anything, just rub it enough to get the Sharpie to come off so we can see the contact area. It looks like to me it wore off the Sharpie pretty evenly on all three lugs. You can still see a little stripe of it down here at the bottom of the lug. So that's looking pretty good to me. It appears that all three of my vertical lug faces are in good enough agreement. Here's another argument for using a slide and barrel from the same manufacturer. They are most likely to be machined in a way for the best lug agreement. At lockup, head spacing in a pistol chambered for center fire rimless ammunition, like the 1911, is defined as the distance from the breech face of the slide to the shoulder in the barrel chamber where the cartridge case would stop. Head spacing is critical to the safe operation of any firearm and needs to fall within a certain range for a given cartridge. It can also affect accuracy. Excessive head spacing can result in inconsistent positioning of the cartridge from shot to shot. Head spacing that is too tight could lead to reliability or function issues. On gunsmith fit barrels, the chamber is usually short and the hood is long. The barrel manufacturer doesn't know how much material you will need to take off the hood. Once it is fit to your slide, the chamber depth needs to be adjusted to achieve the proper headspace dimension. In this case, the hood will be coincident with the breech face, and headspace can be measured from the rear hood surface to the shoulder in the chamber. This is not always the case. Some barrels have a short hood, and at lockup there's clearance between the hood and the breech face. You would have to account for that in your headspace dimension. Let's look at the Saami 9mm case and chamber specs. Case length is from 744 to 754, and chamber headspace is from 754 to 776. That allows for a 0 to 32 thousandths clearance range between the case and headspace dimension. I bought some Saami spec gauges when I ordered my chamber reamer. The go gauge is the maximum case length of 754, and the no-go gauge is the maximum headspace dimension, 776. I've fit the hood to my slide, but I haven't adjusted headspace at all on this chamber. My headspace is 758. So the chamber is already deep enough. My guess is that the chamber in the Atlas barrels is cut to a depth so that it doesn't need to be reamed after it is fit to an Atlas slide. This would simplify and speed up their pistol building process. It locks up with the go gauge and won't lock up with the no-go gauge. So I'm going to assume my chamber and headspace are good to go. It seems I won't be demonstrating this process, but I'll try to walk you through it. First, if my chamber was short, how would I choose what to set my head spacing at? Kuhnhausen states the ideal headspace for an improved performance 1911 is the maximum case length spec plus 5 thousandths for operational margin with the 45 ACP cartridge. If we go by that recommendation, add 5 thou to that max case length of 754 for 9mm, that would be 759. I also measured some 9mm cartridges, not fired cases. The brass generally gets a little shorter when fired because it expands in the other direction, that is radially, to fill the chamber. I measured multiple cases from 6 different kinds of ammo, and they varied from 744 to 752, all within spec but quite the range. Based on that and the Saami case spec, I think I would cut mine a couple thou deeper than that 754 maximum case length, but not quite to 759. I would have probably cut this one to 755 or 756, but 758 is just fine. I'm not really trying to extract maximum accuracy out of this pistol. I mainly want it to run whatever ammo I feed it. I'm sure this pistol, when completed, will still be mechanically capable of more accuracy than I am as a shooter. I think headspace will largely be dependent on the ammo you're going to use in the pistol, your desired level of accuracy, reliability, and tolerance for operational conditions. You need a chamber reamer for this. I bought this one from Brownells. It's a finished reamer for 9mm Luger. It's the only one they had in stock for 9mm, but this is the type I generally see people using for this. The chamber should already be roughed out. Clamp the barrel in a vise, oil up the chamber. Cutting fluid would probably be best. You can put some grease in the flutes of the reamer to catch shavings as well. Carefully insert it into the chamber. We don't want those sharp cutting edges to chip or gouge anything. Turn the reamer slowly clockwise to cut the shoulder deeper. It may also be cutting the taper into the rifling a little bit. Don't put any downward pressure on it, only the weight from the cutter and handle. You can use a T-handle or tap sockets or a wrench. I would recommend using a T-handle. I wouldn't use power tools at all, man. This is a delicate operation. Cut a little, check. Cut a little, check. Remove chips, clean the reamer and chamber, and re-oil each time until you get to your desired depth. Then clean everything up really well. I'll talk about deburring and polishing the chamber later. I don't really think these head spacing gauges are necessary if you have calipers, which are kind of required for this type of project. Check the specs, measure some of your ammunition, give yourself a couple thou more than the longest case. Keep it tighter and use ammunition with consistent case length if you want to maximize accuracy. Now, this is the point where I would fit the final barrel bushing if this were a bushing barrel. Now that our chamber lockup position is defined, it makes sense to me to define the final position on the muzzle end before we cut the lower lugs. If you cut the lower lugs with a slightly loose bushing, the front of the muzzle may be in a slightly different place than it would be with your final bushing. This could affect the lockup fit. There are a lot of different bushing styles out there. Government and commander ones are different length. There are straight bore, angled bore, thick and thin flange. I don't really want to get into that. I'll leave some links to good bushing info that may help you decide in the description. EGW has the largest selection of bushings that I've seen. The slide you purchase needs to be cut for a bushing with the little lug slot. Measure your barrel OD and the slide barrel passage ID. Buy an appropriate sized bushing, one with a slightly oversized OD and a slightly undersized ID if you want the best fit. Let's say my barrel passage is 700 even and my barrel OD is mid-spec at 579. I would probably get a 701 OD bushing with their gunsmith fit 568 ID. They can machine the ID to your spec for extra cost and lead time. I would adjust the OD to the point that I can install it and rotate it only with a barrel bushing wrench. Then oil it up and work it back and forth until it rotates with my desired amount of resistance. You want this as tight as possible if you're going for maximum accuracy. For less accuracy-oriented pistols, I make it a little bit on the looser side so I don't have to use a bushing wrench to take the pistol down. The lug on the bushing OD may need adjusted to match the slot in the slide. After the OD is fit to the slide, adjust the ID until the barrel just slips through it. Put the barrel in, install the bushing in the slide, and see if it can lock up into the upper lugs. If it doesn't, I would start polishing the remaining material off with 600 grit sandpaper wrapped around a nylon rod or something. Check for barrel springing. This is when the barrel hits the skirt of the bushing or binds on some other part of it and prevents it from going up into lockup without slightly bending the barrel or deforming the bushing in some way. Clearance it is necessary as outlined in this diagram. I debated putting this next part in this section or in the link down section, but I think for the best bushing fit and tightest possible lockup, it makes sense to do it now. If it's done now, there shouldn't be any more clearance needed in the ID of the bushing, so the lugs will be cut to match that. Just considering the barrel, bushing, and slide, when the barrel tilts down, push it forward about 1/4 of an inch. You need a minimum of 20 thousandths here. This is critical for link down clearances. You'll need to make this gauge, buy a set for like $6. Take the 20 thou one to a grinder, make it really narrow, deburr, bend it a little. If you don't have 20 thou right here, the interference could be coming from the bushing ID, the bushing skirt, or the spring plug tunnel in the slide. Careful not to open up your bushing ID thinking the interference is there when it may be somewhere else. Sharpie up the bottom of the barrel, install the barrel and bushing, tilt it down, and rotate it, you can see I have marks showing up here and here, meaning my barrel is contacting on the spring plug tunnel here and here, clearance as needed until the modified feeler gauge will go in. A lathe is the best for ID and OD work. Machining the OD is tricky because you pretty much have to have something that holds it on the ID. There are ways to jerry rig it, and believe me, I've done it too. But if you're going to all the work to fit a barrel in the manner laid out in this video, you should probably fit your bushing properly by machining it. Here's a good page from the Kuhnhausen manual about bushing fitting. Pause it if you want to read more. Now it's finally time to cut the lower lugs, arguably the most important step in this process and the one with the highest pucker factor. First, check that the lower lugs or the barrel ramp fit in the cut in the frame. This slot may not be finished in your frame. The Clark Para ramp cut on this Sheely frame seems to be finished, and there is clearance for my lower lugs and ramp. Let's try to visualize what's going to be done here. I have installed my barrel with the barrel holder and the lug centering block. With the slide barrel on the frame, we see material hanging down into the slide stop pinhole. We want to remove material from the lower lugs until the height of this flat spot and the radius at the back match our slide stop pin diameter. Cutting the lower lugs in this manner with the chamber pressed all the way up into the slide will maintain that 100% upper lug engagement at lockup when the slide and barrel are installed on the frame with the slide stop pin. This will result in even contact against both lugs to create that support triangle with the center point of the upper lugs we talked about earlier. This will also keep the barrel from tilting side to side. The rearward location of this radius in the lug, how far we cut it, will determine how far the slide and barrel can come forward on the frame. This is critical for thumb safety engagement and getting this disconnector pocket in the slide in the correct position over the disconnector hole in the frame. I've seen the Hayes Custom guy cut these lugs completely by hand with a file. That requires such an insane amount of skill and experience. A mill could be used to remove most of the material before hand fitting, but a special fixture to hold the barrel would make it much easier. Most of us will use this lug cutter tool. You stick it through the slide stop pinhole in the frame, retain it with this little bushing knob on the other end, and then spin it clockwise as you push the slide and barrel lugs forward into the cutter. There is a 186 cutter and a 195 cutter. I think it's a good idea to use the 186 first, then go to the 195, so less material is removed at a time and less forward force on the slide will be needed. This may result in a finer finish and longer tool life. Slide stop pin diameter spec is 0.1985 to 0.2005. The pinhole in the frame is 201 to 203. Depending on your slide stop and frame, you will likely need to take a little more off after the 195 cutter is used. Let's look at mine. My pin is right at 200. The pinhole in the frame is 202. The lug cutter pilot is 199 and the cutter is actually 194. The cutter pilot and the slide stop pin will rest at the bottom of the hole in the frame. If the 199 pilot sits at the bottom of the 202 hole, that will leave 3 thou clearance up top. I will assume the 194 cutter is centered about the 199 pilot diameter, so that leaves 2.5 per side. So this cutter in my frame should leave about 5.5 thou of material on the lower lug below the top of the pinhole. My 200 slide stop pin sitting at the bottom of the 202 slide stop hole will leave 2 thousandths up top. So that leaves me with a difference of about 3.5 thou I will likely need to take off by hand. Is there a case where the 195 cutter will take too much material off? I did the math, and at either extreme end of the tolerance ranges of the pin, pinhole, and cutter, it will leave about 1 thou of material at the very least. Put the barrel in the slide, center the lower lugs with the block, install the barrel holder, and tighten the set screw. With the frame held securely in a vise, put the slide on the frame, oil or grease up your cutter, Pull the slide back a little so the cutter can be put in. Attach the handle to the slide stop side and insert the bushing on the other side. Turn it clockwise as viewed from the slide stop side while pushing your slide forward. Cut the lugs a little, then take the cutter out and clean off the chip buildup. Oil again, reinstall, and cut more. I would start with the 186 cutter. Go until the left side thumb safety can just be flipped up into the notch in the slide. Then repeat the whole process again with the 195 cutter. Now take the slide off, take out the barrel holder, put your slide and barrel back on the frame, and install the slide stop pin. Push the slide forward and the front of the barrel lug should start riding up on the slide stop pin, but there should just be a tiny bit of material left on the lugs preventing the barrel from locking up. This is where you adjust that last little bit by hand. First, I would use a flat file to take material off the flat spot until your barrel can ride up on the pin. Mark up your lugs with a Sharpie, see where the slide stop pin hits, remove a little more, really sneak up on it. Keep checking where it's hitting with a Sharpie to make sure it's contacting each side evenly. This is an exaggeration, but the lugs may look like this after that is done. When the slide stop pin hits the bottom of that radius where there may be a little step, take a round file of similar diameter to the slide stop pin and cut the radius back until the slide goes all the way forward and the thumb safety can be engaged. You will be removing this last little bit in this step. Maybe give yourself a couple more thou clearance on the front edge of the thumb safety. I used a 3/16 chainsaw tooth file, the diameter of which is a little smaller than the 200 slide stop pin. As I was taking the last little bit of material off, I wrapped 400 grit sandpaper around it, which made it really close to 200 thou. Try not to cut down any more than the depth you did with the flat file, or that will create a little pocket the slide stop will pop in and out of. This filing work is very delicate. Use a flat file with dead edges. Keep the files even across the lugs. Make sure they stay parallel and square. When you get close, it's like 2 file or sandpaper swipes, check, 2 more, and check. The slide stop pin and lower lug relationship will look like this now. The upper barrel lugs will still be at 100% vertical engagement and the slide will be far forward enough to engage the thumb safety. I went a little further on mine, maybe an extra 30 seconds or so the front of the slide and dust cover are flush. I could machine them flush later, but if I don't have to do that, that's preferable. On a short dust cover frame, this wouldn't be as much of an issue. The location of the disconnector pocket in the slide is also critical. You can look and make sure you don't see the forward edge of it. Maybe mark the little no-go area above the edge with a Sharpie. Make sure you don't see any of your Sharpie mark in the hole. You can also take a little scribe or a punch or something and reach in there and make a little mark in the disconnector pocket and then see where it lands. Here's a diagram of approximately what that relationship looks like when the disconnector is installed. When you are done, there should be some extra slide material hanging over the rear of the frame. This could be blended now, but you also want your extractor and ejector installed. I will do this later and show it in a video where I blend everything on the pistol before sending the components out for refinishing. To determine the link length, measure this distance right here on your lower lugs. You want this center bit of the link right here to be the same length. These are old ones I had laying around, of course, none of which were the right size. This is also stated as the correct way to determine link length on page 134 of the M1911 Kuhnhausen manual. Let's look at what happens if the link is too long or too short. Instead of watching me fumble around with some tiny parts, I made a 3D model that will hopefully be better. Right now I have the correctly sized link in this model. This allows the lugs to come up against and sit on top of the slide stop pin, maintaining the same relationship we just established earlier when we cut the lower lugs. If the link is too short, it binds and won't allow the lugs to come forward anymore. If the link is too long, the lugs come all the way forward, but the lugs are being held up above the slide stop pin by the barrel link. This is bad. Our support triangle just went away. The barrel will be unstable and wobbling around on the link if the barrel has less than 100% upper lug engagement. In the case of our barrel with 100% lug engagement, the link would try to force the upper barrel lugs further than they can go. The barrel would bind up between the link and upper lugs. Barrel links are defined by the distance between the center of the pinholes. They are also given a number. This is annoying because we want to know this dimension right here. I created a chart to make this easier. The direct measurement in this column is based on the nominal link hole diameters, so these values are approximate and will vary a little bit based on the holes in the individual link you buy. My barrel is measuring right around 97 thousandths right here. So I will go to my chart and find that value, or close to it in this column. It falls between the number 2.5 and number 3 link sizes. EGW is the one who offers the half link sizes, by the way. Within ordnance spec, there is an allowable clearance range of 1 to 3 thou at the upper link pin and 4 to 7 thou at the slide stop pin. So there may be a couple of link sizes that work fine just because of these loose clearances. I would choose the one that is closest. My .097 dimension is closer to the .0975 than .095, so I would pick link number 3. However, there are two arguments in favor of a shorter link length as it relates to barrel link down, which I will cover in the next section. You may need to ream the pinholes before installing the link and link pin. If these holes are too small, you got to beat the hell out of the pin. You may bend, crack, or damage the lugs, and then you get to buy a new barrel. Brownell sells the 154 reamer for this, but it's never in stock. You can buy it from McMaster. Part number is in the description. It's a number 23 wire gauge reamer. If the pinholes are small, ream it to the correct size. Use oil when you do this and go slow. The Brownell's one has a handle on it. This one doesn't. You might have to get creative. The pinholes in this barrel didn't need reamed. Before installing your link, make sure the one that you selected is the correct length. I would recommend using a temporary pin like a gauge pin or a number 23 drill bit or even your reamer. But put your slide stop pin through, push it back up against the lugs, and the link should wiggle around a little bit. It should be free to move in there. The link isn't doing anything at lockup. My link pin was too tight in the barrel lug holes, so I opened them up very carefully with 600 grit sandpaper. Once the press fit on my pin was feeling correct, I oiled up the pinholes and installed my link. Then I found out the link was in the way of my file when I tried to clearance the lugs for the swing of the link and slide stop pin. So I pushed my link pin out halfway and used the reamer as a temporary pin to clearance the lugs. So use a temporary pin, clearance for the swing of the slide stop pin, then install the link with the link pin. These may need to be clearanced a tiny bit more for proper link down, but we want the majority of it done now. Before installing the link pin for the last time, I also broke some sharp edges on the inside of the lugs that I wouldn't be able to get to with the link installed. If your link pin is loose in the hole, you can stake it in place as outlined on this page. It might be good to confirm that your link is free to move with the slide stop pin up against the lugs as you did before you installed it. This is going to be another long-ass section. Timestamps are still a thing. This is something that has confused me in the past. I've seen a lot of conflicting information. There's even conflicting information between the two Kuhnhausen manuals I have. Anyways, I think I have a better handle on it now and will try to explain it. Link down refers to the movement of the barrel as the action unlocks. The chamber end is pulled down along an arc due to the barrel link pivoting around the slide stop pin as the barrel and slide move rearward together. This pulls the upper barrel lugs out of engagement, allowing the slide to travel rearward by itself and extract and eject the spent casing. Link down ends when the barrel comes up against the vertical impact surface of the frame. Link up is the opposite, and we have mostly determined that by defining our lockup position, cutting the lower lugs, and selecting a barrel link. There's some clearancing we will consider that affects both link up and link down. I've heard link up or link down referred to as cam up or cam down, and this is the camming surface. I don't agree with this nomenclature. A cam refers to a specific mechanical device that rotates and produces linear movement in another component. That's not what's going on here, but whatever, semantics. The static component of link down is that linked down position. What is critical here is where the barrel lugs impact the frame and the clearance between the upper barrel lugs and the slide barrel passage. On an unramped barrel, the location of the barrel ramp in relation to the frame ramp is also important. There is a dynamic part of link down that I think is generally referred to as link down timing. At lockup, the barrel link is not vertical, it's angled slightly forward. Link down is defined as the motion from when the link is vertical until the static, fully linked down position. You may ask yourself, from the locked up position with the link angled forward to where the link is vertical and link down starts, wouldn't the barrel rise slightly, binding it into the slide lugs? Good question. The clearances between the pinholes and pins should account for this. I've also heard link down timing referred to as the clearances that are needed for the dynamic portion of the link down process to occur unimpeded. That pretty much comes down to making sure there's no interference here. Interference here would retard link down timing. The M1911 Kuhnhausen manual includes the Schumann barrel timing test on pages 195 to 197. The whole test is pretty much just making sure you have adequate clearances for the barrel link down motion. And in the linked down position, the barrel is contacting the correct area of the frame. All the clearance numbers I state in this section came from the M1911 manual and the Schumann linked down timing test within it. They seemed reasonable to me. In the fully linked down position, the rear vertical face of the barrel lugs should be up against the vertical impact surface of the frame. There should be no contact here. Doesn't matter if it's a ramped or unramped barrel. On a ramped barrel like this one, ideally we want contact around this circumference, not just a single line of contact, meaning the two mating radii should be the same or very close. At the upper lugs, there should be 10 thou clearance minimum with the slide barrel passage. Link length will affect where the barrel lugs hit the frame. We want them impacting like this on the vertical face with a little bit of clearance above this horizontal surface. If the link is too short or the vertical impact surface is too far back, then they will hit the horizontal surface first. Why is this bad? It will stop the barrel from traveling down, but doesn't stop the barrel from traveling rearward. The barrel will tend to continue rearward due to inertia. This will tug on the link and the link will stop its rearward motion. Eventually this will fatigue and stretch or even break the link. When the barrel lugs hit the vertical impact surface like they ought to, that stops the rearward motion. Then kind of being pinched between the link pin and vertical surface will stop the downward motion. The rearward motion is stopped first and most of the barrel's momentum and energy is transferred into the frame, so the link doesn't see much compressive force as the barrel settles down, taking the clearance out between the pin and pinholes. If the barrel contacts the horizontal surface first, the vertical surface is too far forward, or the link is too long, this may not allow the barrel to link down far enough, resulting in inadequate clearance between the upper barrel lugs and slide lugs. This could result in lug damage during cycling. First, we need to make sure the barrel can tilt down enough in the slide. Barrel hanging in the slide and pushed forward just a little bit. We need at least 20 thou of clearance right here. I already mentioned this in the barrel bushing section. If you recall, the ID or skirt of the bushing may have needed adjustment. I've made myself 3 special feeler gauges for determining upper lug clearance at full link down, 10, 15, and 20 thou thick. I don't have 20 thou of clearance right here. In this case, my bushingless barrel is hanging up on the spring plug tunnel, so I need to remove some material at the corners right here. Check for interference, sharpie the bottom of the barrel if needed, remove material, check and repeat until the 20 thou feeler gauge slides in easily. After I clearanced the rear of the spring plug tunnel area, it was still not dropping far enough and I found contact at the lower edge of the barrel passage and needed to remove a little material there. Next, put the slide and barrel on the frame. Do not install the slide stop pin. Pull the slide back about halfway, push the barrel forward so the bottom of the barrel or barrel ramp is in front of the barrel bed surface right here on the frame. Now we need 15 thou of clearance right here. This should give us 5 thou more clearance than the 10 we should have with the slide stop pin installed, ensuring the barrel stops on the vertical impact surface and not anywhere else. Check that the lug pocket in the frame is cut deep enough. Mine is. I can just look in the front and see it. I know the barrel's not hanging up in the slide anymore. That means the barrel is stopping on the inside of these 2 rails right here. You could confirm this by marking up the bottom of the chamber area and giving it a downward tap to see where contact occurs. I will remove material from these rails by cutting this chamfer deeper on both sides. It shouldn't take much. Conventional wisdom is to clearance the frame, not the barrel. We don't really want to take material off the chamber area where the explosion is happening. Now, install the slide stop. Pull the slide back until the barrel fully links down. Should be able to insert a 10 thou gauge the length of the upper lugs, or about 5/8 of an inch, without resistance. Whether you have the clearance or not, we need to figure out where the barrel lugs are hitting down here in the frame. This will also show us where material needs to come off to get the proper clearance up here if we don't have it. Sharpie the back of the lugs, the bottom side of the chamber or the ramp area here. Get that little radius marked up as well. Reinstall the slide and barrel on the frame with your slide stop. Hold the muzzle vertically. Unlock the action, pull the slide back over the barrel about halfway. I'm going to put a little pressure downward on the chamber area with my thumb. Give the barrel a few taps on the muzzle. Remove your barrel and look at the lug surface. If they're contacting on the vertical impact surface, like you see the marks here, but you couldn't get your 10 thou gauge in, that means the vertical impact is occurring too far forward. Remove the material from the vertical impact surface of the frame. Do not remove material from the barrel lugs. Material should be removed from the vertical impact surface with a mill. There are specific cutters for the Clark-Para ramp and for standard unramped barrels. EGW offers both. To cut the Clark-Para vertical impact surface back, you come in at it this way. For standard barrels, you come in at it this way, and the cutter is extra long to clear the front of the frame. If you don't see a mark on the vertical impact surface, and you do see one here, that means the barrel or ramp is hitting the horizontal frame surface first. Remove material from this surface until the vertical impact surface contacts. In the case of my barrel, it was actually hitting right here on this radius. So I needed to clearance this radius first. Not a lot had to come off. I did need to give myself some clearance with the horizontal surface though, so I brought that one down too. If you don't see a mark anywhere on these surfaces, you may not have created enough clearance in the previous two steps. Go back and figure out what's getting in the way. After every material removal step, check for contact by marking the lugs. Moving the vertical impact surface back may then cause contact with the horizontal surface. Now material will need to be removed here. You may have to kind of chase it around. There will also be a lot of variability in how much material needs to be taken off and where, based on the components and the fit of the individual pistol. There's an argument for a shorter barrel link here. It's less likely that material will need to come off the vertical impact surface, and if it does, it will be less. Or maybe the horizontal surface will only need adjusted, which is generally easier to do. In the fully linked down position, we should have a minimum of 10 thou clearance between all the upper barrel lugs and the slide barrel passage. The lower lugs or ramp should be stopping on the vertical impact surface of the frame, and when it does, there should be a minimum of 5 thou clearance above the horizontal frame surface. This could be confirmed with a clay impression or a feeler gauge. Kuhnhausen lists 3 key points when considering dynamic link down. The first is that a faster link down is preferred, meaning the barrel lugs get out of the way of the rearward traveling slide faster. Fair enough. The link length affects how quickly the barrel lugs disengage from the slide. A shorter link will pull the barrel down quicker due to a tighter swing radius. Yet another argument for a shorter link. I simulated lug disengagement with 2 different link sizes in my model, one 10 thou shorter than the other. With the shorter link, the barrel dropped out of the lugs about 4 degrees of link rotation before the longer link. This resulted in a 25 thousandths difference in slide position at the time of disengagement. Is this significant? I don't really know, but maybe it illustrates the point of what a difference in link length does. Our link length is already set. A link in the middle of the range shouldn't cause any issues. A really long link in pistols with extreme frame rail vertical stack heights will delay link down and possibly cause problems. The second consideration is eliminating any link down interference that would delay or impede link down action. Cool, that makes sense. The third consideration, I don't know that I'm fully understanding it. Retarding rearward slide movement as much as possible. This seems to be an issue with higher energy cartridges. They push the slide back so hard and so fast that they try to overrun the barrel lugs and possibly damage them as they near zero contact and disengagement. A faster link down would help with this, get those lugs out of the way faster, but slowing the slide down would as well. It seems both need to be considered with high energy cartridges. There is a discussion about this in the Kuhnhausen manual on page 192. It relates to recoil spring force, recoil assembly mass, barrel mass, slide mass, and the energy of the cartridge. My main takeaway is that for relatively short or intermediate link lengths and less energetic ammo, it's not that critical. It is interesting to note that the M1911 manual and Schumann test both mention how hard it is to properly time barrel link down with a compensator or sight block. The extra mass out at the end of the barrel is counteracting the tilting motion, and more than that, the slide has a harder time accelerating that barrel mass so the lugs drop out of the way in a reasonable time. Interesting food for thought, but that's all the time I'll spend on this. Our main concern with the dynamic link down action is unimpeded motion. Clearance at the front of the lugs while swinging the slide stop pin. If the lugs bump on the slide stop pin on the way down during the unlocking motion, it will result in a loss of slide velocity. It will also impart some unnecessary impact on the upper lugs, and it will batter the lower lugs and the slide stop pin. This could be considered delaying link down timing. Similarly, if it hits on the way back up, this is called barrel bump. The lugs will bump up over the slide stop pin. It may cause issues with the slide returning into battery, and it will batter the lugs and the slide stop pin. We already checked for this after sizing and installing the barrel link, but we need to check it again now. When checking for this, Kuhnhausen says the recoil assembly should be installed, but using a lighter spring, replicating a more dynamic situation. Sharpie the front of the lugs, assemble and run the slide back and forth pretty hard a few times, check for slap or drag marks, adjust accordingly, and retest until they go away. Once the pistol is test fired, these lugs should be inspected for marks again. With this bull barrel, the recoil assembly is installed in the slide before putting it on the frame. It's not like a bushingless barrel where you can put your guide rod in and then drop the spring in, put your spring plug in through the front. The head of the guide rod comes up against the front of the barrel lug, so it makes it hard to see what contact there might be with the slide stop pin because it already puts a mark on it before you even get it installed on the frame. So what I did is I kept the assembly compressed as I put my slide and barrel on the frame. Link up the barrel and pull the slide back to release the recoil assembly. If your guide rod has a pin in it to retain the reverse plug, you would use the pin instead. You should treat yourself to a toolless guide rod though. Then run your slide back and forth. Pull the slide back and compress the recoil assembly again. Catch it with your toolless guide rod. Then remove the slide. This will prevent the guide rod head from ever contacting the barrel lugs, so you know when contact with the slide stop pin has occurred. Now that I'm done adjusting these lugs, I'm going to go ahead and break the outer edges. There are some other considerations for unramped barrels, like the standard 45 ACP barrels. Since part of the ramp is on the barrel and part is on the frame, it would make sense we would want the ramp as low to the barrel bed as possible while still maintaining vertical impact surface contact. I still think 5 thou clearance here is reasonable, but keep it at that. The barrel ramp edge should be about 1/32 of an inch in front of the frame ramp. A little further is better than a little closer. The last thing may conflict with what I've presented up until now. When the lugs of an unramped barrel impact the vertical surface, we want to make sure we have contact here where the lugs are joined and the strongest. We can also have contact here, but not only here. If there's contact only here, the lower part of the lugs where they are split can be brought forward a tiny bit so they just clear. That seems to me to be the only case where it's appropriate to remove material from the barrel lugs. This is where you would do the final clearance on the side of the hoods for the cut and the slide if needed. Kuhnhausen states 1/1000th per side minimum to ensure no interference and smooth cycling. I've seen as much as 5 thou per side. I kind of fucked up cutting my hood width. I'll explain that in the next part of the video, and I have about 4 per side already, so I'm going to leave it. If you take more material off now, recheck your chamfers and break sharp edges. I didn't have to ream this chamber. I can look down in there and it looks pretty nice to me. I'm not super into polishing chambers.
I will wrap some 1000 grit around something and get in there and just knock off any burrs. This would be a good idea if you ream the chamber. I suppose you could get in there with a cotton buffing wheel and some polishing compound. You don't want to take too much material off because that would loosen the chamber on the cartridge, which would result in accuracy loss. So my barrel ramp kind of hangs into the magazine well a little bit. You can see it's actually kind of like hitting my magazine body right there. I want to take that off. I'm going to check that a round in the magazine is going to hit far up enough that if I bring this flat spot back, the round isn't going to nose into it. Mark it up from the bottom side to see how much needs to come off, and I'll just get rid of that with a file. I'm going to put a little chamfer on this edge, and this edge right here, because sometimes when I'm putting on the slide, they kind of hang up right here as they go back into the ramp cut. Clean up the sharp edges between those chamfers I just cut. I'm going to make sure I have a nice chamfer on the underside of the hood just in case a bullet noses up into it. It'll guide it into the chamber. I would say maybe 10, 20 thou here, then break the edge into the chamber, 5 thou or so. On the bottom, I'm going to break this edge where the cartridge will crest into the chamber just barely. Any material removed here removes support from the case. Kuhnhausen states no more than 2 thou. That was regarding unramped 45 ACP barrels, but I don't think that's a bad thing to apply to ramped barrels, even though these have more case support. I'm not hogging material, I'm not changing the angle of the ramp or anything. There are a few things I'll be doing this barrel, like a flush cut and crown and some aesthetic polishing, but those will come later and they aren't anything required for the process as outlined in this video. That is the fitting process to the best of my knowledge. I hope I captured all the major steps and considerations. Hopefully, not only do you have an idea of what needs to be done, but why it needs to be done. Again, the order of some of these steps could be switched around. There will be some subjectivity regarding how they can be completed. There's likely some wiggle room around the final relationships and clearances between the components that I presented. Please share your thoughts, experiences, tips, and tricks in the comments. Since you saw most of the fitting of this particular barrel as I went through the process in part 1, I'm just going to add some details, discuss challenges, and let you know what I screwed up. If I don't mention a step in this section, it's because it didn't cause me issues or I already discussed those issues in part 1. I screwed up the hood fit. I overestimated the precision of the Z-axis on the mill I was using. It's a mill drill, not a Bridgeport style knee mill. I can better account for this on future machining projects. Setting up the barrel in the vise was a pain. I had to use an indicator and sweep across the little flat part of the lugs and ramp area. I would make or buy a jig next time, the Everglades Ammo one probably. I assumed the cut for the hood was centered in the slide. It's not. It's offset towards the ejection port. I'm guessing Atlas did this because centering it would create a knife edge with this tri-top face right here. The hood material that needed removed was offset. I took too much material off this side and incorrectly assumed very little or none needed to come off this side. I needed to take about 25 thou off. I figured I would take 24 off the thick side and be fine. I ended up taking too much off, didn't leave any for hand fitting. Also, a bit more than I thought of that 25 needed to come off the other side. I machined the hood length and left 1 thou. This was easier to do because the feeding was on the x-axis, which is much more stable than the quill. When I got to fitting the hood by hand, I was feeling for tightness to know when I was getting close to the correct hood length. This is part of the process you can't get a feel for unless you do it. I didn't have a very good feel for it. Since I didn't take enough material off the one side of my hood and too much off the other, my hood material was offset with respect to the slide slot when the barrel was centered in the slide. As the hood started going up further into the slide, it was binding up as the chamber tried to center itself in the barrel passage. I mistook the tightness due to the improperly cut hood width for tightness on the length. I figured it out and took material off the other side of the hood so it wouldn't bind up, but the hood length was about 2.5 thou short by that point. The hood width clearance is sloppy. That's not critical, but I'm bummed about the 2 thou on the length. Will it negatively affect accuracy as it matters to me, or the longevity of the barrel? Probably not. Cutting the lugs with the tool was pretty straightforward. I think doing it in steps, the 186th and the 195 cutter, was good. It didn't require as much forward force on the slide, likely easier on the cutters. On the way in, the barrel lugs kind of skipped over the cutter and left a slightly raised, wavy surface in front of the radius. I tried to go back and cut it again, more slowly, but it didn't clean up. I guess there was a tiny bit of flex somewhere in the system allowing the lugs to spring up over the cutter a little bit. Not a huge deal. That area was taken off during hand fitting anyways. I think this is an argument for less forward force on the slide when cutting. I see Brownells sells a lever to wrench the slide forward. I wouldn't recommend that. The little shavings and shards that came off the hardened stainless barrel lugs were nasty. Watch out for those. That's not a kind of sliver you want. Hand fitting of the lugs was difficult and nerve-wracking. Not one of those things you can get a feel for without doing it. I went really slow, checked a lot. It turned out fine. I got the slide and dust cover flush at the muzzle. The disconnector pocket is where it should be. Thumb safety engages. The vertical lockup feels tight. All good. My lugs right here measured really close to the number 3 link. I ordered the 2.5 as well. There's 2.5 thou difference between those 2 link lengths, which can be accounted for with the link pin and hole clearances. They both passed the wiggle test, so I picked the shorter number 2.5 link. I think this helped me with the link down frame contact because I didn't need to touch the vertical impact surface. This is a very difficult, time-consuming process. So many steps and little details, lots of ways to screw it up. I learned a ton. It would obviously go much smoother if I were to do it again, but there's still so much room for me to develop these skills. I could probably do it 20 times and still learn something every single time. I'm pleased with the fit of this barrel. Is it amazing or really good? No, it's good for my current skill level and better than I thought it may turn out. I know this is an obscenely long video, but I wanted to keep all the information in one place. I didn't really intend it to be consumed all at once. Hopefully the detailed timestamps will make it easier for people to navigate to the information they're looking for. I hope it does contain most of the information needed to understand the 1911 barrel fitting process, and if not, some sources in the description may be a good place to start looking for what's missing. The rest of the videos in this double stack 1911 build series should be shorter and come out a bit more frequently. The individual projects are a bit less involved. Whether you watch this whole video or only a small part of it, thank you. I appreciate it and I hope it's helpful in some way. I'll catch you next time.